How are you?
Thanks so much for the introduction, and thanks also to Joans, Antonio, and Francisco for inviting me to give this talk. So I'll tell you about non-reciprocal effects in photonic systems and topological effects. And I would like to start by saying a few words about Lorentz reciprocity, just to refresh this idea. So we say that a system is reciprocal, photonic system is reciprocal, if you can interchange the positions of a source and of a receiver. And when you do that, for example, if you go from A and B, if you interchange them, the transmission level remains the same. So if this happens, the system is reciprocal. And if you would be new to electromagnetics, this would look like something that would happen only in very special circumstances. For example, if your system has some kind of spatial symmetry, so that if you look to left or to right, they look the same. But actually this property, it's the rule, not the exception. So most photonic systems have this property. And this property makes the systems bidirectional. The transmission level is the same. So you transmit, if you transmit very well in one direction, you also transmit well in the other direction. Sometimes this is good. Other times we would like to break this reciprocity, because in some instances you would like to have systems that, for example, just allow the wave to go in one direction. And this happens, and it's used commonly in, for example, if you want an optical isolator. Imagine you have a laser, very high power source, and you want to protect it from reflections from the load. If the load is mismatched, it is bad if the power comes back to the laser, because it may destroy it, it may affect the operation. And so people use these optical isolators. And the way to break the Lorentz reciprocity typically is to use a bias magnetic field. You put a static magnetic field, and you can make the system propagate just in one way and have this interesting feature. Now, the problem with this typical solution is that these systems, first of all, to have this biasing circuit, when you have this magnetic field, it can be very bulky, so it can occupy a lot of space. So, of course, people don't like this. It's difficult to integrate with modern technologies. And also, these systems tend to be very long, because the non-reciprocal effects at optics, they are quite weak. So, actually, sometimes people say that an optical isolator at optics has the same physical length than an optical isolator at microwaves, because the effect of the non-reciprocity is quite weak. So people in recent years have explored different solutions to have non-reciprocal effects, strong non-reciprocal effects at optics. And I'm going to tell you about a particular solution that we developed recently, and that allows you to have this without magnetic fields. Okay? And to build up on this idea, I would like to start with something that may look a little bit exotic, which is to look at moving media. So imagine you have bodies that are moving, and you want to study the electrodynamics of this type of systems. So let me mention just from the beginning that when you have moving bodies, and for example it could be well, in the simplest case it could be, for example, imagine you have a metal sheet and it is moving very fast for some reason. When you have this type of system, this system is non-reciprocal. I'm not going to use it immediately. I'm going to tell you a little bit more about this non-reciprocity a little bit later, but just to make context with what I want. And so the system I want to study, to begin with, is this system where you have two metal sheets. They are neutral. So on average, there is no charge. Each of them is uncharged. And one is sliding over the other. And actually, this problem, we looked at it about 5 years ago, something like that. And at the time, we were rather fascinated with the problem that Professor Pendry told a few words in the end of this talk, when Joans asked some question, this problem of quantum friction. And we were studying this problem, and we asked, what happens from a classical point of view? Is there anything interesting from a classical point of view happening in this system when you have two metal sheets sliding over the other? And it seems there is nothing especially interesting. I'm imagining no light source, no excitation. It's just a mechanical problem. It should be solved with standard Newton's law, if there is anything to solve. But actually, if you make, as sometimes happens when you make a question, you get some surprising answer. And so if you are curious to find what are the photonic modes supported by this type of system when you have motion. And it's a simple problem to solve. It's basically a Fabry-Perot cavity. You can imagine that you have an air gap, like here, and you have your your metal sheet that is not moving, and this one is moving at velocity v, and you want to compute the modes of this system. So it's some sort of, you recognize this as the standard dispersion equation for a Fabry-Perot cavity. So if you start with the wave here, it has to propagate a little bit to get to the upper interface. It is reflected, and then it is propagates again, and then it is reflected again, and so you have this. There is just one tiny thing that you need to worry, because one of the bodies is moving. One of the reflection coefficients for the bottom one, you have to compute it at Doppler shifted frequency, because the body is moving, so it will not see the same frequency as in the lab frame. It will see a Doppler shifted frequency. So if you solve this, and let's assume to begin with that there is no loss, what you would expect for a lossless system to find is that the modes should be should have real valued oscillation frequencies. Okay, they oscillate with some frequency. And so you end up with a little surprise if you solve this, because actually you find, when you solve the problem, and this is a specific example, so this is for a velocity of motion. Let me tell you already that these are very large velocities. So this is for a velocity of the order of, I didn't write it here, but I know it's around 0.1 c. And you put some small distance between the two slabs, and actually here I consider the loss, in the realistic loss in silver. And if you solve this problem, you find that your natural frequencies will be complex valued. And this would be true even if I don't consider loss. So if I consider loss, of course, I expect to have some complex valued frequencies, because the modes should decay with time because of absorption. But the interesting thing here, so here I'm plotting real part of the frequency, and here it's imaginary part of the frequency, and this is the interesting one, and this is the wave number, and the wave is propagating, let's suppose, along x. And what you find, what you get is this type of bubble diagrams, and the interesting part of the bubble diagrams, it's the top region, where you get imaginary part of the frequency positive. And you also get imaginary part of the frequency negative. So this already tells you that there is something strange happening. It cannot be in the two possible semi-planes. And actually, if you see, this corresponds to solutions that grow exponentially with time. So what electrodynamics tells us is that in this simple problem, when you have two sliding bodies, you can actually have some type of lasing, so spontaneous emission of energy. So where is this energy coming from? This energy comes from the kinetic energy of the moving slab, and actually it's a spontaneous conversion of kinetic energy into light. Okay, and so there is some sort of instability developed in this system, and everything is fine with the conservation of energy, because at the same time there will be a friction force, in this case classical friction force, that tries to slow down the moving body, and so basically it develops some work on this body. Okay, so this is my starting point. So let me mention briefly, you can also have this with rotating bodies, and if you could do this in the lab, or if you could use this for any practical application, it would be quite nice. You could have lasing with this type of systems. Of course, we cannot do it because it's so large velocities, you cannot do it in the lab. Maybe in some astrophysical scenarios, this type of systems can be interesting, and actually people that work on plasma physics, they study related problems. But a few years ago, we were kind of wondering, can we somehow imitate these moving systems in some platform that could be actually done in the lab? Okay? And so we came up with this idea that what if, so I told you about moving slab, one of them is moving. What if we just imitate this motion, this physical motion of the slab? Instead of having physical motion, let's consider instead that we just inject electrons in one of the materials and create a drift current. So you can do this simply by applying, you put here a voltage generator, and so you get a DC current. And this DC current, from this simple analogy, you expect that maybe this system will be similar to this system. And actually, it turns out they are quite similar. And so basically, you can get related effects or comparable effects in the two cases. So even if this is true, it's still quite challenging, because actually to have strong effect, you need velocities that should be comparable with a fraction of the velocity of light. 0.1 c, sometimes you can get 0.01 c. It's still very challenging. And the velocity of electrons, for example, if you look at silver, they don't go that fast. It's very, very, very much lower than that. So we try to think which platform could be good for this, and one obvious solution is to use graphene. As you know, in graphene, it's very large mobility, which means if you apply electric field, the electrons will go actually quite fast, and they can have velocities compared to the Fermi velocity, which is c over 300. It's still quite low value, if you notice. I was talking about 0.1 c, so it's quite challenging. And so we came up with this proposal to have some kind of lasing, but in this case using graphene. And so basically it's, you see here 2 graphene sheets. One of them you don't enforce any drift, and the one on the top you just connect it to a DC voltage, and then you have drifting electrons going on the top, okay? And we expected to see some sort of instabilities similar to the moving medium case. And actually this is what happens, but let me first tell you how we can model this, how can we treat this system. And so the first thing you need to know is, if you want to solve the problem from an electromagnetic point of view, you need to know what should be the conductivity of this graphene sheet with drifting electrons, okay? And so we computed this conductivity, and we do this by taking into account the drift, and we take into account modifying the microscopic Hamiltonian of graphene. We put some interaction term responsible for the drift, and then using linear theory, Kubo theory, we can compute the self-consistent response, and we get the conductivity. And it turns out the answer is simple. It's not too complicated. It's simple. It's not complicated. And basically you find that the conductivity with drift, it's related to the standard conductivity without drift through this simple formula that you see here. So this is the usual conductivity without drift, what people use in plasmonics to solve in graphene plasmonics, and this is the conductivity with drift. And mainly there are 2 differences compared to the usual case. First of all, you have to replace the frequency by the Doppler shifted frequency. Makes sense. The electrons are moving. And the second thing, which is important in what I'm going to tell next, it's this prefactor. So you have to multiply by the frequency and divide by the Doppler shifted frequency. So this factor, actually, it has an interesting consequence because this is conductivity. Conductivity, if it has a real part, means loss, means dissipation. Okay? But because of this prefactor, you can, if your V0, if your drift velocity is sufficiently large, you can make this factor negative. So if you have actually a velocity larger than the phase velocity of the wave, you can have a real part of conductivity that is negative. So it's exactly, so if it's negative resistance means it's gain. It's what we want. So we want to extract energy from these drifting electrons. And it is what happens, and we named this effect negative Landau damping. And let me tell you a little bit more about it and motivate it a little bit more intuition about this effect. And for this, we consider some electrons, some test particle, under the influence of some electric field like this one. It's a free particle, and so it's just this simple equation of motion. And let's assume that this free particle goes with some initial velocity. So if this velocity is not very large, in some scale that's not very important, this oscillating electric field will not do much. In half a cycle, it will accelerate the particle, but in the other half, it will deaccelerate. So on average, the particle goes with the same velocity, always the same velocity, it's not increasing. Things get more interesting if you start considering large drift velocities, and if you solve this equation. And so let me show you what happens if you have a drift velocity that is a little bit less than the phase velocity of the wave. And so in this case, what happens if you compute the position of the particle as a function of time, and then you subtract what would be the displacement without electric field, V0 multiplied by t. The particle starts with V0, and so this, if there would be no electric field, it would be 0, but with the electric field, you see that the particle goes a little bit faster. So actually what is happening is that the particle is gaining energy from the wave. So from the point of view of the wave, it's some sort of dissipation. And so this is the standard Landau damping, which was discovered many years ago. And so basically in this case, the particle gains energy from the wave. The situation changes if you consider instead the situation where the velocity of the particle is a little bit larger than the phase velocity. In this case, you find that actually the particle goes slower and slower. So basically it is losing energy to the waves. So in this case, instead of absorption, you have gain, so the particle is losing kinetic energy and emitting it in form of radiation. So in usual materials, this is the mechanism that dominates, because most electrons will feel this situation, so you have Landau damping. But if you inject the current in your graphene, you can put many electrons with velocities larger than VPF, and then you can have this mechanism to dominate, or in some conditions at least. And so you can have this gain. And so actually, so if you use this model, you find that analogous to the moving medium, indeed, you can have this instability, so you can have lasing or spacing, as Mark Stockman proposed to name this lasing with plasmons, and you can have this, this type of bubble diagrams, and the important one is that you see the imaginary part of the frequency of the modes can be positive, so this tells you that you can have instabilities. Okay, so let me also show you very quickly the field profiles of this unstable mode. So basically they are analogous to plasmons, so this is what you see here. So basically they decay exponentially. And it is interesting to compare what happens. So this is a plot of the longitudinal component of the electric field. Without, and the arrows is the pointing vector, and you can see that without drift, you just have the normal plasmons, in this case in bilayer graphene, and the energy goes along Z, but along X, I'm sorry, along this direction, propagation. But with the drift, actually you see that there is a transfer of energy from this sheet, so the one with the drifting electrons, to the other one, okay? And so you have this gain. So, now, so this is a very, I said, a very specific problem where I want to have lasing, but this is not necessarily the only application. In fact, this one I think can be more exciting. You just consider now, instead of 2 graphene sheets, just consider 1, like this. And you still bias it with the drifting electrons. So as I mentioned previously, this system, by the way, will be stable. There will be no instabilities. To have the instabilities, you need to have the interaction between the 2 systems. Otherwise, you don't get them. So this one will be stable, which does not mean it is passive. It can have some gain, but is stable. And we noticed that this is a non-reciprocal system because it has a broken time reversal symmetry from the point of view of electromagnetism. Because if you reverse time, the system that you get is the same, but with the velocity of the drifting electrons flipped. And so we studied what would be the wave propagation, the plasmon wave propagation in this platform. And, well, again, we use this conductivity for with the drift current, and basically are the usual equations. If you are familiar with graphene plasmonics, it's exactly the same equations. We just use this drift, and it is non-reciprocal, as you can check explicitly by looking at here. And this is what you get for this plasmon's dispersion diagram for propagation along X, the direction of the drifting electrons. So if you don't have any drift, it would be the black line. And you see it's symmetric, so left and right, of course, are exactly the same. But as soon as you put the drift, you break the time reversal symmetry. You also break a parity symmetry, as can be easily seen. And so you can have very asymmetric dispersion of the plasmons. So the plasmons that go to left and the plasmons that go to right, they feel things totally different. And what happens is that the drifting electrons tend to drag the plasmons in their direction. So the drifting electrons go in this direction, and they like the wave also to go in this direction. So basically you can get regimes of, for example, for very large velocities of the order of VF, like in this purple line, you can get regimes that you just have one mode propagating, so you don't get the second mode. So the wave can only propagate to the right, not to the left. The wave is dragged by the plasmons, if the plasmons by the drifting electrons, if the drifting electrons go sufficiently fast. So this is quite exciting. But by the way, you don't need necessarily these large drift velocities to have unidirectional propagation. Because even if you work, let's say we work near this 20 terahertz for the blue line, even if you have 2 modes, what I show here is the ratio between the attenuation constant of the 2 modes, the one that goes to the left and to the right. And you see that even for relatively small frequencies, so this is for the blue line case, it's this curve. And you see that the wave that goes to the left is, even if that mode exists, it's always more attenuated than the one that goes to the right. So effectively, we have some type of optical isolator, but at the nanoscale, so you can use it at the nanoscale, and with the length can be the length of maybe 100 nanometers, you can have a very good optical isolator with graphene. You don't need these bulky systems with, at this frequency, they would have lengths of the order of maybe 10 microns, so maybe 1,000 times bigger. So let me mention briefly that other people before us also look at these plasmons in graphene, specifically in this article by the group of Polini, but they didn't study this unidirectional propagation. They just look at the non-reciprocal response, but they didn't analyze the unidirectional features of these platforms. So another interesting thing, very briefly, is that the plasmons with the drift, they actually go they propagate more than without the drift. And this is what I illustrate here. I compare the propagation length with drift and without drift for the same characteristic size of the plasmons. And as you can see, in some cases, you can get gains of the order of 4. So one way to explain this, oops, sorry, what did I do? One way to explain this, I think I pressed the wrong button. Thank you. Thank you. So one way to explain this is because of this negative Landau damping that gives you some gain. It's not clear from, basically we're just computing the dispersion equation, but this may be one of the reasons, or maybe just because you change the dispersion, we are not totally sure. But what happens is that indeed they can propagate more, at least that's what the equations show. So let me show you what happens if you put an emitter, a vertical emitter on the top of the graphene sheet. And if you don't have, so this is some kind of vertical dipole, and if you don't have the drift, you see that it emits in both directions. But if you put the drift for these velocities, so in this case Vf/2, Vf/4, you see it only emits to the right. It does not emit to the left, or it emits very weakly, because the plasmons that go to the left, if they exist, they are much more attenuated. And so the SPPs are dragged by the drifting electrons, and you can see here a time animation of these plasmons. So another thing that we look at very briefly is what happens if you put an obstacle. So in this scenario you have your emitter, and now we put obstacles in the path of the wave that is launched, and what we expected, and it's what I'm going to show you, is that because there is not this backscattering channel, the propagation is much less affected by the presence of the object. And so this is without drift. And the object is, this is the emitter, this is your obstacle, and in this case it's two obstacles. And you see that with the obstacles, the plasmons barely can go further, but if you put the drift, which is here, so for single and two obstacles, the plasmons can go. The intensity of the field is much stronger than the case without the obstacles. It's not a perfect, let's say, it's not like in topological systems that everything must go if there is no loss, because graphene has loss. So actually, even though the wave is not backscattered, there can be some little dissipation here, and also it is also possible to emit modes to the bulk, to the dielectric. But anyway, it's much better, and you can see the time animation, and you can compare, and it is actually much better. So let me make a partial summary. So basically what I showed you is that this graphene with the drift current can be a very interesting platform, because you can, first of all, it can be an active material, and so this raises all kinds of opportunities. And second, you can use it as some sort of optical isolator. I mean, this is for the Earth. And it can have many advantages compared with systems, for example, with magnetic fields. Okay?
Mario, can I ask you something?
Oh, sure.
I'm wondering, are drift velocities that are any considerable fraction of the Fermi velocity realistic? Or in other words, what is the highest drift velocity compared to the Fermi velocity that anybody has ever observed in any system?
That's an excellent question. So the feedback I have from Frank Kompens, so actually we discussed this with him, and he told us that we can run into troubles if you consider velocities more or less greater than Vf/2 because of thermal effects. He says that up to Vf/2 in principle should be doable.
Because to me this means that the Fermi sphere in momentum space shifts by a very considerable fraction of the Brillouin zone.
Well, it's you are right. There is some shift. There is some shift. I don't know. I don't think people have experimentally demonstrated this. But let me mention, for example, that in electron gas, for example, this problem of the instabilities. People have looked at instabilities when you have an electron gas, and they can have with velocities that actually are a little bit smaller than graphene. You can get some instabilities, and so if you can get instabilities, I think it's much easier to get this, for example, unidirectional propagation. So I believe it can be done, but I don't have an answer to give you better than this. So, yeah. But I hope someone tries to do it, and hopefully he will show it is possible. So okay, so this was the first part of my talk, and in the second part of the talk I'm going to change a little bit the topic, still talk about non-reciprocity, but now from the point of view of topology, topological photonics. And I'm sure most of you heard about this previously, about topological photonics, so it has been a topic that has gained a lot of attention and momentum in the last 10 years. So a few words about topology. You say that two objects are topologically equivalent if you deform them somehow and there is some property that stays the same. For example, in the theory of surfaces, this property is the number of holes. If you deform a surface, like, for example, if you look at this line, you can deform this surface. If you don't do anything dramatic, which is to create holes or close holes, the number of holes is always the same. So we say it's topologically invariant. And so this is a global property. You can, locally you can change a lot, but in terms of global terms, this property stays the same. So it turns out that these invariants, they also appear in other contexts, and actually in physical systems. And I want to focus in photonics. And in photonics, you cannot look at, so it turns out that materials can be topological. You can have materials, and you can say, you can classify them topologically. Say that this material, you assign an index, 0, 1, 2, 3, minus 1. So in this case, this number, you cannot just look at the material and see what is the topological number. But basically, there are mathematical methods, and there is a mathematical way of counting the number of holes for a material. And it is called the share number. So I will focus on this non-reciprocal topological materials. And so this was first proposed, I believe, by Haldane and Ragu. And they showed exactly what I'm saying, that if you have a photonic crystal, and actually it does not need to be a photonic crystal, but if you have a photonic crystal, you have a band structure. Imagine you have a complete band gap. So these topological materials are operated in band gaps. They don't propagate, no states in the bulk. But in this band gap, you can calculate some number of holes. So it's the share number. It's the gap share number. It will be an integer. Okay? And so according to this theory, you can say if the two materials have the same topological number, they are equivalent. If they don't have, they are not equivalent, of course. And you compute this from the band structure. This topological number, you obtain it from the band structure.
15 minutes. Okay.
Sure. Okay. So what we do with this topological number, this topological number allows us to predict if you have two of these topological materials, mirrors, they don't support propagation. If you put them together, the difference between topological numbers will be the number of states that are supported at the interface. So if you put these materials, they don't support propagation, but if you put them together, you'll see modes propagating at the interface. And they will be unidirectional. So the difference gives you the number of modes, the net number of modes that propagate at the surface. So let me illustrate this with an example. And I'm going to consider, for simplicity, a continuous material, no periodicity. It is just an magnetized electric plasma. So if you want, it's a Drude metal. And you put a magnetic field. And so the response becomes non-reciprocal and gyrotropic. These formulas, if you are curious to see. And this is the band structure. Frequency, wave vector, and this is propagation perpendicular to the field, to the bias field. And using these tools that I told you, you can compute these shared numbers. And you find that you have two band gaps. You have two interesting frequency regions, the one on top, the one on bottom, and you find, for example, the one on top as this topological number 1. And so according to this theory, if we put this magnetized plasma next to a trivial material, and the trivial material could be just a metal, not magnetized, then you should have one edge state in this gap. Okay? And this is exactly what happens. I show you here the interface of a perfect electric conductor pack and this material, and consistent with this bulk edge correspondence, you get exactly just one mode propagating. It's kind of similar to graphene, but this one is more powerful, the graphene with drift bias. This one is more powerful because this is strictly topological. And so if you don't have loss, for example, this is a simulation. This is the pack on the top. This is your magnetized plasma. If you put here a source, similar to the graphene case I showed you previously, only waves going to the right can be excited. But in this case, they are exactly protected against any form of backscattering. If there is no loss, the wave cannot go here, cannot go back, and cannot be absorbed. So it is forced just to go. So this is, of course, it's quite exciting. It's unidirectional system. And it's robust to all this type of craziness. You can corrugate the surface as you wish. If there is no loss, it still goes. Of course, there is loss in real systems. But so the question I want to look at, it's so this shared number, it can count the number of modes. That's what people have been doing in the last 10 years. But I want to ask a different question: is does this photonic shared number have a different physical meaning, something more powerful? And the motivation for asking this question is, if you are familiar with electronics, and many of these concepts, they come from electronics. This shared number appeared in electronics when people were looking at the all conductivity. If you have an electron gas, magnetized electron gas, you find that in some conditions, the all conductivity is quantized, and the quantum is the shared number. So which means that, for example, if you change the magnetic field, the all conductivity should vary in steps. So sometimes you change the magnetic field and the conductivity does not change at all. It's constant. So it can only change in quantum. And so the electronic shared number, C, is the quantum of the all conductivity. But we don't have a conductivity, a photonic conductivity in optics. So this does not help us much. So what I want to ask is, does in optics, can we find another physical meaning for photonic shared number? Some quantity that is quantized, that is not obvious. And so this is what I want to discuss, and I will show you that yes. And so to do this, let's look again at this slide, and I want to find one question. What is the key feature of these topological materials? Of course, it's that they propagate and continue to go. And sometimes people are curious, okay, what happens here in the end? So for example, in this simulation, it's an open boundary, so the wave just goes. And sometimes people ask, okay, but now if you close the system, what's going to happen if you close the system? And what is going to happen is that if you don't have loss, the wave must continue. And so if you close the system, for example, like I'm going to show you here, and here is my source. If you close the system by putting PC all around your material, basically your wave is forced to go and circulate around the cavity walls. Okay? And so this is a very important property. In this type of topological systems, if you close them, the energy is forced to circulate around the cavity walls. And I'm going to show you that this has an important implication in terms of angular momentum of this system. Because if the wave is rotating, there should be an angular momentum. Now, I want to go one step further. In this simulation, you see that there is here an excitation. And so basically, you are pumping energy into the cavity and make it circulate. I want to go one step further and remove the source. So I remove my optical source or my microwave source, whatever it is. And I want to ask what happens in this case. So I consider a closed cavity filled with this topological material, and I don't put any source. So if I don't put any source, it may seem nothing happens, nothing particularly interesting happens, but of course there is still radiation in the cavity because thermal effects and quantum effects. So if you have a cavity is made of matter, so of course thermal effects will make atoms jiggle, so there will be radiation, there will be absorption. In thermal equilibrium they are the same, and because of this there is some noise in the cavity, some electromagnetic noise, if you want Nyquist-Johnson noise. Now, I discussed that this non-reciprocity and this topological properties makes the mode circulate in a classical setting. So what happens when you consider light that is generated just by thermal fluctuations? We'll get anything of the sort? Will we have some kind of circulating noise in the cavity? And it turns out it is exactly what happens. So basically we'll have, I'm going to show you, we'll have some circulation of this in thermal equilibrium, we'll have a circulation of this thermal energy inside the cavity. So to analyze this problem, you can analyze it in many ways. Usually the tool that you would use is the fluctuation dissipation theorem to compute whatever you are interested in inside the cavity, some correlations of the fields. But I'm going to consider for simplicity the case where you have very little loss. And in that case, you can just consider a model expansion. You can think that in your cavity, basically what you have is the classical modes. Each mode corresponds to a harmonic oscillator. And in thermal equilibrium, the energy of that harmonic oscillator will be determined by this formula, which is Bose-Einstein statistics, the mean energy of the harmonic oscillator. And so I want to see if there is any energy going around the cavity in thermal equilibrium, which is something very strange. And to characterize this, what we do is we compute the thermal expectation of the Poynting vector. It's the heat current. And you can do it by taking into account the contribution of all the frequency channels. So you have many modes in the cavity, each one with some frequency. So each one of them will contribute something to this integral. And this density of the heat current, it can be written simply in terms of the modes, by just noticing that each mode is one channel, so it should have contributions only at the frequency at which the mode oscillates. And then basically you have to multiply it by the Poynting vector of the classical mode, and the energy associated with the mode, it's this determined by the Bose-Einstein statistics. It's just this. So from this formula, it may seem very puzzling that you can have this heat circulating inside the cavity, but from this formula you immediately see that you must have it, because this cannot be zero. If, for example, you consider a frequency in the band gap where you have this only one mode circulating around the cavity walls, just one, there is no way there is any cancellation. It's just, for this frequency, there is just one contribution to this integral, to this sum, okay? And so basically, yes, we can have this circulation of heat inside the cavity. And let me show you the results for this specific geometry. It's a parallel plate waveguide. This is exact calculation. So basically, we compute exactly the modes of the system. Or if you want to use the fluctuation dissipation theorem, you get the same result. And this is the result that you obtain for the density of the Poynting vector for some frequency in the band gap. And you see that on the top wall, the heat circulates to the right. And by the way, this frequency, the modes would also circulate, these topological modes would go to the right. And on the bottom wall, the heat circulates to the left. So basically what you get is, because of the non-reciprocity, you get the circulation of heat in closed orbits. So you force the heat to circulate, which is rather puzzling and rather unusual, let's say. So some properties. There is no problems with no paradox, no breakdown of fluctuation electrodynamics, because it turns out that the divergence of this the expectation of the Poynting vector is zero. So this means that the heat is circulating, but it's in closed orbit. So you just make it circulate. You are not having any source, any sinks or any sources. So there is no net transfer of heat from one point to the other point. It's just a circulation, okay? And the second property is that you can have this non-trivial heat current only if you break the reciprocity. So only if you have a broken time reversal symmetry. And by the way, let me mention that about the same time, the group of Shen Weifan also showed something different, but not for topological systems. Okay, so let me now focus on this angular momentum, and I'll show that the angular momentum of these systems is something really interesting and remarkable. And of course, since the heat current is going in closed orbits, there should be an angular momentum, and it should exist even at limit of zero temperature. In that case, it's from the quantum fluctuations, the 0-point quantum fluctuations. And if you want to characterize the angular momentum, basically we do the same. If you want fluctuation dissipation theorem, we split everything in terms of some density, and the formulas are a bit strange, but the contributions for the angular momentum density is basically a sum of overall modes. And now I'm not going to show you I'm not going to show you the derivation, but I'm going to tell you the result. And it's really a very short derivation. It's very simple, but I will show you the final result. So I'm trying to see what should be this angular momentum density. And if you think about angular momentum density, I mean, it could be anything. It could be any number. Because, for example, if you change the magnetic field, angular momentum density should change continuously. If you change the microstructure, the angular momentum density should change. If you change the period, if you change the dispersion of the materials, the angular momentum should change. So it should be any number, should have not any particular feature. But actually the interesting thing is that you find that if you make the cavity sufficiently large, it does not have to be very large, but the result is exact when the cavity has a very large cross-section. By the way, this is a 3D system, it's not a 2D system. You find that the angular momentum density is given by this simple formula. I see here some little problem with fonts, but it's given by this simple formula. So divided by the area of the system, it's just determined by some very simple physical constants. C, speed of light in vacuum, this, which is the Bose-Einstein statistics. Sorry, it's this one. I don't know why it's different. And then this C. C just counts the number of edge states going around the cavity walls, okay? Which is the Scher number from the bulk edge correspondence. So this is a quite powerful result. So it tells you, for example, if I change the magnetic field continuously, if it's not a drastic change, the angular momentum will not change. Okay? This is similar to the electronic case where you change the magnetic field continuously and the conductivity does not change. It's only in steps. Here it's the same. And so the Scher number has this powerful physical meaning. It is the quantum of the angular momentum. So very briefly, I know I'm running out of time. So just a very quick example. And I consider the same as before, but now it's a circular cavity, finite radius. And when it's a circular cavity of finite radius, you see that the modes, they come in finite numbers. So for example, in this band gap, you get 16 modes. In the other band gap, you get 8 modes. It's these dots. If you make the cavity very large, you get the green line, which is what you'd get for a planar type interface. And so what you find, for example, in this case, Scher number is -1. Scher number gives you the quantum of the angular momentum. The sign of the Scher number tells you if the angular momentum is positive or negative. And you get the positive angular momentum when the Scher number is negative. And this is what you see for a mode in the first gap. It is going anti-clockwise. The Scher number is negative. Let me just show you quickly how does the angular momentum density varies. Well, this is as a function of frequency in the band gap, in the first gap. And this is the normalized angular momentum density. And it should be an integer to be quantized. And I'm considering different radius for the cavity. And you see that for a small radius, 10, it's relatively small actually. It's close to this quantized value. If you increase a little bit more the radius for 20, it's even close. And of course, if you make the cavity sufficiently large, it will be exactly 1. So it's exactly quantized. So my last slide. Just a few words. So I believe that this can actually be measured. And I believe the one way to measure it is, for example, you have a microwave cavity with one of these topological materials. There are several ways to do it, for example, with ferrites. And as I told you, there will be the circulation of heat around the cavity walls. And if you want to detect this, what you can do is to put here a directional coupler, and you can move some of this energy. So if the energy is circulating in one direction, this direction, let's say, you can design the coupler to make more energy go to port B than to port A. So you can detect this circulation of heat in closed orbits by seeing the difference between power going to port A and port B and showing that it is different. And if you calibrate your system, you can even see that it's quantized. Okay? So just a small note, you can only see the thermal part of this angular momentum. So to see the thermal part, you must break the thermal equilibrium. So this means that A and B cannot be at the same temperature as the cavity. You must, because otherwise there is no flow. The Poynting vector lines are closed, you would not be able to measure anything. So in summary, just two brief conclusions. I showed that surprisingly this non-reciprocity can create this circulation of heat in closed orbits in very general context. And the second interesting thing is that the shared number can be understood as the quantum of the angular momentum. Thank you.